Thank you for joining me today on this webinar for Denitrifying Bioreactors. I am Keegan Colt, the Executive Director for the Agricultural Drainage Management Coalition. This webinar is part of a series of webinars that was partially funded by an agreement with CTIC through the EPA Consultant Training Grant. This is one of 6 webinars, the others being the impacts of drainage on crop production. Today is denitrifying bioreactors, saturated buffers, drainage water management, navigating the NRCS website, and then taking a look at a special case study on conservation drainage installation. Over the next 30 minutes, you'll learn a lot about bioreactors. First and foremost, you'll learn what a bioreactor is, where do bioreactors work in the landscape, design considerations that are needed to be known to actually facilitate the design of the practice, how they are constructed and installed, and then finally take a look at the cost effectiveness of the practice in terms of cost per pound of nitrogen removed. A little background on ADMC. We are an industry-led member coalition. Our founding members are a lot of the tile manufacturers and distributors out there, as well as the software companies that support the drainage contractors, the drainage contractor organizations themselves like Leaky, and then individual contractors, and then state commodity groups and the engineering groups that help design these practices are all members of ADMC. Our mission with ADMC is pretty straightforward. We're an industry-led partnership that's really looking to find practical solutions to improve water quality and agronomics through managing drainage systems. So we know the benefits of drainage systems. We do know there's unintended consequences that are associated with drainage. So we're really trying to find practical solutions that not only develop the practical solutions or practices to make available to the farmers and landowners, but figure out ways to speed implementation of these practices. So stepping back to review, in case you did not sit on the first webinar of this webinar series, the benefits of tile drainage, I think these are pretty well known. The biggest being maybe the earlier planting dates, making sure that field's dry enough to be able to get out there in the spring when you want to for timely operations. And not only earlier planting in terms of drying that soil down, but also it gives you that confidence that's needed sometimes when you switch over to soil health practices like no-till systems and cover crops. Gives you the confidence that that soil is going to dry out with no-till and be ready to plant early in the spring and warm up in time. As well as cover crops, it helps establish better stands of cover crop, as well as that timely termination of the cover crop in the spring for your primary crop. Just like in the spring, where we can get better planting conditions, it also helps ensure better harvest conditions later in the fall. It takes away compaction issues by drying that soil out, especially with that heavier equipment that's associated with harvest. Less wear and tear on that equipment as well if it's drier field conditions, and sets you up for a better next spring without that compaction. Decreases crop damage, and this is really by eliminating or helping to reduce excessive moisture. Looking at RMA's crop insurance payouts on a yearly basis, excessive moisture and precipitation is one of the leading causes of crop insurance claims. And this is why we're seeing farmers looking to install tile already as a risk mitigation practice. And moving forward, we're going to be seeing more and more of that. On the flip side of that, drought is also one of the higher payouts for crop insurance on a yearly basis all over the United States. And actually, there are some water management practices like drainage water management that can help you combat some of those droughty issues that we'll talk about in a later webinar. One of the more underutilized reasons why tile drainage is being used, or maybe least recognized, but it's there, and we're starting to see more studies come out on it, is the improved nitrogen use efficiency in drained landscape versus undrained. So drained landscapes are shown to be able to produce the same amount of crop with less amount of nitrogen that's needed on it. Or if we put that nitrogen in there, we can get more production out of that same pound of nitrogen, get more pounds of crop off the field with it. Also, it gives us a little bit of confidence. It gives us more confidence, I should say, not a little bit. It gives us more confidence in what we apply to being available to the crop, so we can really narrow in those nitrogen application rates That agronomic optimum nitrogen rate is shown to have a narrow band with drained versus undrained. And so we're not as subject to year-to-year variability when it comes to how much nitrogen should be applied to that field. Decreasing that amount of nitrogen that's needed to grow that crop increases that energy efficiency of that crop production, so it decreases the energy needed to produce the crop. Also, we do see things like better gas mileage or fuel efficiency from the equipment moving across that field if it's a drier field versus one that's slipping in those wet soil conditions. All this leads to improved profitability, and that improved profitability leads to increases in the land value. On the other hand, with drainage, we know a lot of the benefits of drainage to the production system. From the environmental aspects, we know that drainage can be a conduit to move dissolved nutrients from the field to surface water bodies. And really, this happens at all levels, the farm level, especially if you're watering livestock off of those local streams or water sources, or if you have a farmed well, that can be a concern of too high of nitrate concentrations in that farm well. Locally, the drinking water sources, communities rely on surface water bodies for their drinking water or very shallow wells. In Iowa, for instance, the most famous case is probably the Des Moines Water Works, where they sued upstream communities because of their drinking water source, the Raccoon River, was exceeding the maximum load or the recommended 10 parts per million for drinking water, and that obviously is a very high concern. And so that's why we're trying to figure out these practices that can work with those drainage systems and pull down those nitrate concentrations. Then moving on to regionally, the Gulf of Mexico, the hypoxic zone, the dead zone in the Gulf of Mexico impacts the fishery down there, as well as other areas like the Chesapeake Bay, where we see their TMDL being written. All of these lead to needing to figure out ways to bring that nitrate load that reaches these surface streams down. I always like showing this slide from Dr. Castellano from Iowa State University. The red line there, that first red line that you see is the rate of soil nitrate production from native soil organic matter. So basically, when are we converting that organic matter that's out there in that soil into nitrate that's available for the crop? Also, it's water soluble at that same time. And that green line shows us when the crop is actually ready to utilize that nitrate. You see those two peaks don't line up. And if they did, we would not be having nearly the concern or issues that we are having with nitrate from our crop production systems that we are having right now. But since they don't line up, kind of the gap in between those two peaks really represents a time where we're vulnerable to losing that nitrate from the system and causing unintended consequences downstream. So when we look at the bend of production versus the environment, that overlap, we think there's a lot of room for conservation drainage to work with that production system in mind, but also to produce those environmental outputs that we want to see. When we talk about conservation drainage practices, when I go out and speak to various groups, there's quite a suite of practices. There's not just one practice. Drainage water management, which is another webinar in this series that you'll hear about, automated drainage water management now with automated control structures for that is a great one. Today we're talking about bioreactors, saturated buffers, it will be another episode of this webinar series later on. And then there will be sub-irrigation and drainage water recycling, constructed wetlands, or sometimes referred to as water quality wetlands, two-stage ditches, and multi-purpose oxbows. So there's a lot of different practices out there available in the suite of conservation drainage practices. So what is a denitrifying bioreactor? Well, bioreactor is an edge-of-field tile treatment practice where part of that water is diverted through an underground bed of wood chips. This diagram here drawn by John Peterson, courtesy of Matt Helmers at Iowa State University, shows how we get that water in and out of the bioreactor. So we have two control structures. That top control structure diverts the flow from that field tile, introduces it to that bed of wood chip. There's a distribution line at the upper end. It flows through that bed of wood chips all the way to the lower end, where there's another control structure that has stop boards in it once again to really control that speed of flow through the bioreactor. It's collected in a distribution line at the bottom end of the bioreactor and reintroduced to that field tile at this point and lets that treated water outlet into the main and eventually outlet to the stream. Where do these bioreactors work? Right now, bioreactors are typically going in on drainage areas that are anywhere from 30 to 100 acres, although we are starting to see bioreactors go in on larger drainage areas, upwards of maybe 250 acres. That's probably about the max. Anything larger than that, you maybe should be considering practices such as that water quality wetland, constructed wetland type options. Maybe you could do some work up in that tile shed and try to connect some of the sub mains before they reach that larger main. In order to treat that water, you could do bioreactors in line upstream in that situation, or maybe drainage water management would work further upstream if you do have those 300 plus acre drainage areas. When we're looking at bioreactors, we want to know that that tile has consistent flow. Even though it's an extremely cost-effective practice, it isn't an expensive practice to consider. And there is a 10-year maintenance interval where we do need to replace the wood chips. And so you want to know you're putting it on a tile that's going to have consistent and good flows coming through it. At the same time, it's great if you can get a few water samples from that tile line to ensure that you actually have a tile that contains high nitrogen. Anything over 10 parts per million probably warrants treatment. Definitely, if you're that 15 to 20 parts per million or higher, definitely a bioreactor would be well suited for that situation. But if it's a tile line that generally does not carry very high nitrate concentration with it, perhaps there's some other practices that you could consider instead of a bioreactor where you're not going to have that 10-year maintenance interval on it. Bioreactors are kind of the generalists when it comes to where they fit in the landscape. They're very flexible in where they'll actually work. And so a lot of times we'll go out to farmers and producers and the landowners to try to find sites for saturated buffers, first of all, because they're a little bit easier to deal with in a bioreactor. And site selection for saturated buffers is a little bit more specific, which you'll hear about in that webinar. If they're not suited for a saturated buffer, usually a bioreactor is a backup, and we do find landowners are interested in bioreactors still. But once again, they'll fit into more sites than what saturated buffers or even constructed wetlands will fit in on. Also, we're out there in the landscape looking where to put these bioreactors, having some grade associated with that main, and so some kind of relief in the elevation of that field and filter strip. Really, it makes things a lot easier. At least a 1% grade to work with is great. That grade really helps you push water in and out of the system, so you can get a higher amount of water to flow through your bioreactor instead of really slow, kind of stagnant water there. If there isn't grade, there are starting to be pumped bioreactors now, which is interesting. There's actually studies to show that if you kind of wet dry bioreactors, you can kind of supercharge its effectiveness because you make more carbon available to those microbes that utilize that wood chip as its food source. And then, of course, once that wood chip is saturated and the whole condition down there is saturated, they start utilizing nitrate for their metabolism. And so if we go from wet to dry, it makes more of that carbon available to those microorganisms. That might shorten the life expectancy of the bioreactor. That's why we really want tiles with consistent flow over the years instead of having longer stretches of dry periods. But it could make it more effective overall. Bioreactor placement. When bioreactors first came out, we were really looking to put bioreactors kind of only in those filter strips next to a stream edge where there's an outlet to the stream, or maybe another body of water, and we would make bioreactors work there. Now we're finding that we can actually place bioreactors further up in the landscape, not necessarily along the stream edge, but along field borders. So, like I mentioned before, you can connect on submains, entering into a larger main in some of these drainage district areas. And as long as the landowner is willing to dedicate the treatment area that's involved, about 100 feet long by 20 feet wide for the bed of wood chips, you can make them work in that landscape position. Some other things to think about when we think about where to put bioreactors. we don't want to have surface intakes involved. If there are surface intakes, we want to make sure there's steps being taken to prevent sediment from moving down into that tile system, because we don't want that sediment to plug the bioreactor distribution line or even the wood chips themselves. So if there is a surface intake, it needs to be protected, by a nice grass filter strip around it. Maybe it's a blind inlet or some other steps that you can take. You do want to be careful, if it's a intake behind a terrace, that tile system, really warrants treatment. If that tile system really only drains that terrace and kind of serves that purpose to get that surface water behind the terrace out of there, you generally don't have a lot of nitrogen in those types of situations. So it's not really worth the added step of doing the wood chip denitrifying bioreactor, because that water that moves to the subsurface, that's where we're picking up the nitrate in that tile load. You also want to have a good conversation with the farmer and landowner about what the future site plans are. If this isn't a filter strip, is that filter strip going to be here in 10 years or not? Is that CRP contract coming up? If it's at 100 feet wide and it's going to get knocked back down to 30 or something like that. So you just want to know what the future plans are for the site. You can make it work. Sometimes you can turn bioreactors sideways, so they run parallel to the stream, and so then they can fit in a pretty narrow band. And that's a good idea to do anyways, a lot of times, just in case, somebody wants to reduce that width of that filter strip in the future. Also, is there going to be new tile going in, or is this main going to be the same size moving forward? Is there any thought at all about maybe if it's an 8-inch main, bumping that up to 10 or a 12-inch main in the future? You could always get the control box larger and make it work for future conditions. But if it's a smaller control structure and then that main gets upgraded, that would become a choke point. You don't want that to happen. So just having that conversation to make sure we know what that tile is going to look like for the next 10 years. Also, you need to avoid areas that are prone to flooding. If you're at the end of a grass waterway or somewhere, you have a lot of surface runoff or surface water moving across the top of it, that's not an ideal situation. And if you're next to a stream, and that stream's really flashy or has a seasonally high water table for a lot of the spring, that's probably not the best spot to put a bioreactor, because that water table comes up, and in those wood chips for extended periods, we won't be able to actually push any water through that bioreactor like we want to. So it's a missed opportunity for treatment. So just knowing, what that water table does on an annual basis are really good things to consider when looking at site selection. Design criteria. So how do we actually figure out how big the bioreactor is and how it'll work? Probably most importantly, we need to know the size and material and the grade of that main. So the characteristics of that main really establishes how much water that system will carry and how fast that water will be moving through the system. Also, you need to know where that water is coming from. So the contributing area of that tile. So if you know what all that tile, how far that tile goes back from the stream, how many acres comes into it. When looking at the design, you can do it for a 1/8-inch drainage coefficient, and that's if you know the whole contributing area, or you do it for 15% of the peak flow of that based off of the characteristics of your main. Most of the time, the 15% of the peak flow ends up being the more cost-effective size. That 1/8-inch drainage coefficient for the contributing area generally generates a little bit larger of a bioreactor. Next, with the wood chips for the bioreactor, the wood chips are really what make the magic happen. I mentioned earlier, it provides that carbon source for microbes to utilize. We saturate that condition. We saturate those wood chips. That takes that oxygen level down low. And so those microbes that are down there need to find something besides oxygen to breathe, to metabolize the carbon in the wood chip. And so they go to the next easiest thing, and that's nitrate in the system. And so that's how they convert the nitrate to just N2 gas, is that saturated condition. So when we look at wood chips, what are we looking for? It's very important that you know your source of wood chips beforehand, and if it's an NRCS project or any project that meets your approval before they are coming to the site, nothing's worse than having your contractors there with the pit open, ready to go, and then having the wood chips show up and they're not the right type of wood chips, or it's just not the right material, and you have to turn that semi-loaded up chips back, and it just puts everybody behind schedule. It can get pretty costly pretty quick when that happens. So we look for a chipped material, not shredded. They are starting to look at shredded options, but that's really not into the standard as of yet. You can probably do it if you tweak your design, but more often than not, chipped is safer right now. It'd be nice in the future if we could start moving towards a shredded material, just because that's more readily available, especially with municipal piles being out there. And generally, they're a little bit less expensive than the chipped material. But for now, the safest bet is to use a chipped material. The size of the wood chip, generally 1 to 2 inches in size. They can be a little bit bigger, a little bit smaller, but if you're in that ballpark of that 1 to 2 inch size, that's what we're looking for. Anything smaller, it's really hard to push that water through the system, or it gets harder to push water through. Anything larger than that, then there's actually too much space in between the wood chips, and the water goes too quickly through the system, and we don't get the treatment we want to see. You don't want an older pile of chips. You kind of want to know that it's fresh. You don't want the wood chips breaking down already. Those should be avoided if it's very obviously been decaying and sitting around for a long period of time. You don't want to have a lot of dirt mixed in with it. There's always going to be dirt and fines in a pile of wood chips, but if it's too much, then you should look for a different source. And also, you don't want to utilize any species that are naturally resistant to decay. You want those wood chips to be able to break down, and so if it resists decay, it's not going to break down. It's not going to have that carbon available to spur denitrification. So, avoid a cedar-like species on that. The treatment area, about 80 to 125 feet long, 15 to 25 feet wide. That's really a good conversation to have early on with the landowner to say, hey, do you have this amount of space that you would be able to dedicate to the bioreactor? You can work within filter strip programs, so a lot of times you don't even have to take additional land out of production. It's just a matter of making sure that you have that footprint to work with. Looking at the installation, you set your control structures. It's also a very good idea to have an outlet established before you start digging your pit, just because if it's a wet year and water starts filling into your pit, you want somewhere for that water to be able to go. You don't want that water to get in the way of a good quality installation. You excavate out your pit. It's almost like making a big basement. You match the depth of that tile main generally on that bioreactor pit. You'll slope it a little bit just to get some grade in the pit. But for the most part, you match the depth of that main. You don't want to go deeper than the main because you want all the water to be able to get out of that bioreactor on that lower end. So wherever your outlet elevation is, you don't want to be below that outlet elevation on the floor of your bioreactor. The deeper you go, the more expensive a bioreactor is. So, generally, if it's a 4-foot deep tile, that's kind of a typical depth. All of a sudden, if you're looking at 6 to 8 foot depth, that really adds up your excavation cost pretty quickly, as well as that wood chip cost. Once you have that nice basement dug, you can go ahead and put your wood chips in. Utilizing a walking floor semi-trailer, I think, works the best. You can back it right up to the pit, especially if you know you have stable walls, and they can pour those wood chips right into the pit for you. The contractor can utilize their excavator to feather and spread those wood chips out. The design will have a depth of wood chips that's needed. Really, that depth, the most important thing is to make sure we're not going to get too much overburden on that with the soil cap that you put back on top. So once again, if you're at those deeper bioreactor sites where that main's 6 to 8 feet down, you're probably going to have 5+ feet of wood chips in there, just so you're not putting up 4 feet of topsoil over the top of that. If it's a 4-foot tile, you're generally looking at about 3 feet of wood chips. You want about 18 to 24 inches of overburden on it. Anything more, compaction may become an issue where you might compact those wood chips too much and not get the flow that you want through the wood chips. I always say order about 10% more of the wood chips, just in case you get a little wide on one end from your design specs, or you're a little bit long. Also, it's not a perfect science on filling and loading these trailers up with wood chips, so you might get a little more, a little less than you wanted to on a given load. If you're ever running short, I always say go deeper on the top end or the inlet side and shallower on the outlet side, just because that's kind of the gradient that the water's going to flow. And so, we're not going to have that equal depth all the way across. Generally, you're not going to actually fill up 3 feet of water within the bed of the bioreactor bed. So if you are starting to run short, maybe try to get by going a little bit shallower on that outlet side. Next, you cover it up with a geotextile fabric. That really just keeps soil from moving down into the wood chips if you utilize the soil cap. Not every state utilizes the soil cap. Illinois, it's pretty common, just have an open pit bioreactor where you just bring wood chips all the way to the top and you just dispose of the soil back into the field. Iowa, most of the time we're seeing the soil cap being utilized. Here you can see the soil is put back over top of that geotextile fabric. Then it gets reseeded. If it's in a CRP, you follow the CRP seeding plan. Otherwise, you can just put any grass out there, and you really don't notice where these bioreactors are once the installation is complete. You might see a little compaction or where decomposition happens with those wood chips. You'll see some settling where you'll get a little bit lower. So it is important to kind of mark where this is at, so you're not going to be driving over it, and hopefully no one falls into it if it is settling. Looking at the cost effectiveness of these bioreactors, $15,000 is about the average install cost. With that, even though it is $15,000, a big price tag, they are very effective at removing nitrogen. So it's about $1 to $5 per pound of nitrate removed, which is very cost effective when you compare that to other practices and how much they cost per pound of nitrate removed. That's why bioreactors are a tool being utilized in a lot of the nutrient reduction strategies out there. This is just a graph compiled from the data from the Iowa nutrient reduction strategy. For bioreactors, they really looked at studies from across the Midwest that's kind of comparable to Iowa, the performance of those bioreactors, and they noticed about a 42% nitrogen load reduction. I always go back to the percent load reduction, in my mind, is not the most important number. I'd be more concerned with the overall load reduction. If you're on a larger system, you're probably not going to get 42% reduction. You might only be getting 20% reduction, but that 20% is actually going to be a much larger nitrogen load just because you had so much more opportunity to treat. So once again, getting on those tile systems where you're going to have that consistent flow for longer stretches of the year with that high nitrogen really make bioreactors more cost effective. Next, I'm going to show you a video from the SWCS Conservation Media Library. It's a great, real general overview, and it'll kind of reiterate a lot of the points we had in today's webinar. And it'll give you some nice visuals on the actual construction of the process and how that denitrification works. And I think it will give you a very clear idea of how this practice works. So give me just a second to adjust my
Woodchip bioreactors. There's still a little mystery in exactly how they work. Once one is installed, just like the water in the underground tile it treats, you hardly know it's there. That's the nature of a woodchip bioreactor, one of a number of options conservation-minded farmers are using to reduce the amount of nitrates in water leaving their farms. It's no secret that extensive tile drainage of low-lying soils has boosted corn and soybean production by leaps and bounds across the Midwestern United States. But an unfortunate byproduct of that productivity boom that's becoming more evident is high nitrate levels in the tile drainage water. Woodchip bioreactors are getting more attention because tile waters routed through them show cuts in annual loads of nitrates from 15% to 60% on average, and in some cases even more. Woodchip bioreactors are placed near the outlet of a tile line on the edge of a field. First, a pit is dug to the depth of the tile. Sizes vary, but most are about 100 feet long and up to 30 feet wide. An inflow water control structure is connected to the tile line to route water into the bioreactor. A second water control structure is installed at the lower end of the pit. A perforated tile connected to the water control structure at the upper end of the pit will distribute water evenly across the bioreactor, and a second perforated tile at the lower end will gather treated water and direct it to an outflow water structure. The pit is then filled with wood chips. The chips are covered with a geotextile fabric to separate the wood chips from a topsoil cover, which is seeded to grass. Here's what happens underground that you don't see. When small gates are lowered into the water control structure at the upper end of the bioreactor, tile water is redirected through the perforated tile into the bioreactor. In times of high flow, some of the tile drainage water will bypass the bioreactor and flow to the original tile outlet. The water control structure at the lower end of the bioreactor controls how fast water moves through the wood chips. Gates are lowered to the structure during higher flow to raise the water level in the bioreactor and slow the water flow long enough for denitrification to take place. That happens when bacteria, fungi, and other microorganisms living in the soil colonize the wood chips, using the carbon in the chips as their food and convert nitrates in the water to harmless nitrogen gas. There's still a lot we don't know about bioreactors, like how long they will work and how to maximize their ability to remove nitrates. But their advantages are clear. They are small and can be easily installed. They're placed at edges of fields so they don't take any cropland out of production. They can be used at sites where targeted nitrate removal wetlands can't be installed, and they can be used with other nitrate removal technologies. Bioreactors are relatively inexpensive to install and may qualify for USDA conservation cost share assistance. They don't require much maintenance. You hardly know they are there. Put one in, and it begins to remove nitrates immediately with the first water flow. Well, that's the short story on the bioreactor, the practice that's not seen or heard, but naturally does its job to improve water quality for us all.
Yeah, so that's a great video there. It gives a very good review of what we talked about in this webinar today about how bioreactors work. And I really hope that that visual there gives you a clear understanding of what they do. Just a quick summary of today's presentation. And while I'm talking about the summary, you can go ahead and try to use that QR code to get to a short quiz, if you will, to assess your understanding of bioreactors and what we talked about today, just so we know if what we were saying, if that was effective or not to the participant. So bioreactors, very briefly, utilize those wood chips to spur denitrification. We introduce water into those bed of wood chips by diverting tile flow into them. Generally, they're about 100 feet long, 20 feet wide. They're kind of the generalist practice when we're talking about edge of field practices will fit in many different landscape positions. But it does require grade to be effective. So if it's completely flat, you'll have to think about pumping and not just utilizing the control structures. Performance varies on bioreactors, but overall they're very efficient. They found to be very efficient. About 42% of the nitrate load is estimated to be removed on average. Sometimes that's higher, sometimes that's lower. And once again, I don't think it's necessarily bad if it's lower, because a lot of times that means we're treating a higher amount of load, even though the percentage is a little bit lower. If you'd like to further interact with ADMC, feel free to reach out to me via email, follow us on Twitter. Of course, you can always become a member of ADMC. We do have a new $125 affiliate level to join our organization to keep supporting the work that we're trying to do. But if you visit our website, you will have a pop-up if it's the first time you visited in the last year to sign up for the Conservation Drainage Weekly. And that's a very good opportunity to receive once a week, just information on the latest in conservation drainage. So a lot of the new research that's out there, also implementation activities, different events, and other learning opportunities for conservation drainage practices. With that, I'd like to thank you for completing this webinar with me on denitrifying bioreactors. Look for the other 5 webinars that are part of this series with CTIC through their EPA Consultant Training Grant. And thank you to CTIC for working and partially funding this project with ADMC.